Ready?
Okay.
Now we are online.
So our situation is very similar to the previous two. So we have a railway interlocking system that we are developing. It is a classic three-layer system that consists of the upper layer with operators' workstations and data servers and so on. The programmer logical
Can you move
controllers.
a bit the screen of the laptop on that side? Okay, thank you.
Okay. So programmer logical controllers that are calculating the main logic and the controlled equipment. So what does this system do? This system controls the stations of the underground. So it controls switches, it controls lights, signals, it obtains trains position, it generates control commands to the trains, and performing different service tasks that should be performed on the station. So here is the scheme of the station. If you're interested, we have in our experimental field 6 switches that can be either this way or this way. So the train can go either this way or this way. So we have signals that can be red, blue, green, or something else. So and we have the system that is performing this task. Initially, we've used Linux with the Preempt RT patch on operator workstations, and its performance we were satisfied with its performance, and we tried to use it also on the programmable logical controllers. It is an experimental system at the moment. It is not functioning on the station, but during the tests, it's performing very well. It is a completely synchronous system. So it is a completely synchronous system with very simple architecture. So the cycles, so the time is split into cycles, 100 milliseconds each, relatively long cycles. And during each of cycle, several processes should perform their operation. In order to do this task, we created the driver for Linux kernel that is providing several dev files. So this is providing read and write operation on several dev files, and unblocks these operations according to the predefined schedule. So this is how the just the example of just the accept of the main cycle of this driver. So it so this cycle is performed once per cycle, so once per 100 milliseconds. And for the dev files that we created, it sleeps for the defined for the predefined range, then unblocks the write operations, and then the process that was blocked on these operations is getting unblocked, performs its operations, and let's go. So the user space processes have strictly defined priorities, so that we can guarantee that the process 2 here cannot execute unless the process 1 is completed. All these features are provided to us by Preempt RT, and the performance is pretty fine for us. So that's mainly it. So what we require most from it? So we require the precision of those moments of task unblocking. So after the sync event on the millisecond number 65, this one must be unblocked, and the precision is very important for us. The second thing that is important is the priorities. So this process cannot start because it uses until this one is finished, because it uses data generated by it. We have a bunch of measures of protection from the fails that may happen. If it is interesting, I mean, we talk about them in details. But the general architecture, the general system, satisfies us very well. The problem that we have is the processing of network packets. So when we're doing, so our system, so I didn't talk about this, our system is connected with each other with CAN buses. So like in the automotive domain. But some information exchange between the PLCs and operational workstations, database service information exchange, is performed by the Ethernet. And the predictability of network packet processors is not satisfying us. The next thing that we are protecting ourselves at the moment by using the hardware that is much more powerful that is actually needed. We would certainly like to consider but the possibility to reduce the power of hardware we are using. And this is where shared deadline may help us, because at the moment we are more or less happy even without it. But when in some applications we need to use less powerful hardware, and that is where we're looking for shared deadline assistance. So that is it.
Okay, thank you. Any questions?
Yeah, so what particular from the network is the problem? Is it the Linux network stack architecture that's the problem with the soft IRQ-based packet receive and all that nonsense? Or is it purely a scheduling issue?
I would suggest that this is a scheduling issue. Maybe we are doing something wrong here, but when our process is involved in where the system is involved in heavy packet processing, the predictability is decreasing.
Yeah. So the Linux network stack has been a problem for a while for real time. Mostly because the Linux network stack is built for throughput, and it's hooked into
yes, and it's the opposite too. Yeah.
Yeah, it's hooked into the soft interrupt stuff that we have, and it's basically pulling and batching as much as it can, which is not good for latency issues at all.
Oh yes. That exactly is an issue.
Yeah. Sorry, but with preempt-RT, the soft IRQ thing should be executed in the hard interrupt context, in the hard IRQ thread.
So yeah, we've run it in the hard IRQ thread, but the whole network stack is still structured the same. We have had thoughts of ripping the network stack apart, but that's a lot of work. Mm-hmm. And nobody's really wanting to do it, only then to be told by Dave Miller to go someplace, the sun don't shine. So yeah, there's not a lot of progress there.
But do you know? Should we expect it, or we just should compose our systems, accepting that
the hard interrupt comes in. Mm-hmm. In the preempt-RT, that wakes up a thread that runs the hard interrupt handler, which for networking.
Yes, exactly.
That then kicks the soft interrupt bit, and then we run the soft interrupt handler, and that basically pulls the hardware for packets. And that
those are the yeah. Mm-hmm.
And then it processes these packets and sticks them in the sockets, and then waits whoever is waiting on these sockets. Mm-hmm. But that might be a whole while later. So what you want for real time is
predictability. Yes.
The packet comes in, you immediately multiplex it through the socket, raise that signal, and then make sure that the task that was waiting on that socket gets to run and process that packet, and then go to the next packet. So strictly FIFO, strictly direct route, from the hardware towards your processing. But that's not how Linux stack works.
There was a question.
Can that be achieved by playing with the NAPI weight?
I'm not
With,
sure.
I'm sorry, with what?
The NAPI weight.
Mhm, okay.
Basically, it processes packets in bars. If you reduce the size of the bars, maybe the performance will be
It's
better.
been 7 years since I looked at the network stack in too much detail. Things might have changed a bit.
Yeah, maybe
Not so much.
because I played with that a little bit for the real-time Linux workshop in Lugano, and if everything is properly configured, performances didn't look too bad. Of course, you need a lot of configuration with the interrupt priorities, NAPI, weight, and so on. Otherwise, performance, yeah.
So yeah, one would be for someone who has done this to write it up and maybe share with the rest of the RT community. And another is Thomas and Meany to find Dave Miller and beat him up.
So it may even be not the embedded Linux stack. Maybe we can replace somehow with our, because we don't need the whole this bunch.
Yeah, so I don't know the CAN stuff too well, but I know Thomas was using that works for the CAN stack. Only a few months ago, he basically had to rewrite some of the CAN drivers because they weren't SMB safe at all. And they were crashing the machine and all that.
Okay.
Made him decidedly unhappy. But if you're willing to do that, you can write your own custom stack. I mean, it's not too hard if you write it just for one particular piece of hardware. Just get the intro, get your data out.
Expect we'll end up with this, yeah.
And dump it to the application that needs it. If you can then show that that works and show and share the code and show the Linux networking people why their stack sucks, that would be good.
Can't promise, but yeah. I think.
You know, if you've heard of anybody trying to get something like the OWIP, that pre-canned GPL stack, up and running as a user space, I've tried to track someone down to them with that.
So that's the user space.
The user space network stack.
I have heard of that, and it came up recently. So Andy Kling from Intel was doing a batch set on the networking stack to reduce size, and that was in the light of the Internet of Things and Intel's Quark architecture. I think there's a tiny little CPU that I wish Intel would have never done, because since they're new for these bitches, and I'm really happy they've gone. I'll snuck around. So he was slimming down the network stack, and Dave Miller basically tore him a new one. Says, well, all this stuff is needed and required, and I don't want the maintenance burden of the exponential configuration option explosion you're generating and all that. And people said, well, the alternative is pushing the entire network stack to the user space and doing a user space thing. And they gave some numbers that was an entire TCP stack in like 4K text. So yeah, I know people have been playing with it. I know the InfiniBand people also tend to do stuff like this.
They do strange things in
RDMA people, yeah. But it has been done.
Okay.
Any other question or comment? So I think we can thank you very much.